There's a machine right now, at this very moment, screaming into the darkness of interstellar space, and almost nobody on Earth is paying attention to what it is saying. It is not screaming loudly. In fact, the signal it sends back is so impossibly faint, weaker than the power it takes to light a single holiday bulb on a Christmas tree, that it takes the largest radio antennas humanity has ever constructed just to barely hear it. But it is still there, still transmitting, still sending back data from a place no human being has ever been, from a place no other machine in the history of civilization has ever reached. And what it has been finding in those outer dark regions, in those final, desperate, power-starved years of its extraordinary life, is something that scientists are only beginning to process. Something that rewrites what we thought we knew about the universe waiting beyond our solar doorstep. The question nobody is asking loudly enough is this: what exactly did Voyager 1 find out there, the cold unknown, before its lights finally began going out one by one? Voyager 1, NASA's deep space probe, is currently the farthest spacecraft from our planet, exploring interstellar space at a distance of roughly 15.8 billion miles from Earth. Read that number again, 15.8 billion miles. That is not a poetic approximation. That is not science fiction. That is the literal, measured, calculated distance of a machine that human hands built, that human minds designed, that launched from a Florida launch pad in September of 1977, when disco was still playing on the radio and the concept of a personal computer was barely imaginable, and has been flying continuously without stopping ever since. For nearly 50 years, this spacecraft has been moving away from us at 38,000 miles per hour, and it is still going. And here is where it starts to get strange, because what Voyager has been finding out there, in that region of space that no textbook had ever properly described before, has surprised even the scientists who built the instruments doing the measuring. But before we get to what it found, we need to understand what it was walking into. Because the story of Voyager's final years is not just a story about a dying machine. It is a story about the edge of everything we know and what happens when you actually go there and look. For most of human history, the boundary of our solar system was a theoretical concept. Scientists knew that the sun generates an enormous bubble of charged particles and magnetic fields, a kind of protective cocoon that extends billions of miles in every direction. They called it the heliosphere. Everything inside it, every planet, every moon, every asteroid, every comet, exists under the sun's electromagnetic jurisdiction. Everything outside it belongs to something else entirely. The question was always, what is that something else? What does the universe actually look like when you step outside the only neighborhood any human-made object had ever known? And here is where Voyager's story stops being just remarkable and starts being genuinely astonishing, because the answer it sent back was nothing like what was expected. In 2012, Voyager 1 officially crossed into interstellar space, becoming the first spacecraft ever to send data from outside the solar system. That crossing alone was a milestone so profound that it took scientists more than a year to confirm it had actually happened, because the environment at the boundary was so alien, so unlike their models, that they kept questioning their own instruments. Think about what that means. We had built mathematical models, run computer simulations, constructed entire theoretical frameworks about what the edge of our solar system should look like, and then Voyager arrived there, and reality looked different. Not slightly different, substantially, uncomfortably different. As Voyager crossed the boundary zone at the edge of the heliosphere, both Voyager 1 and Voyager 2 detected a searing hot region of space where the sun's influence ends and interstellar space begins, where temperatures spike to an estimated 30,000 to 50,000 Kelvin. A wall of heat at the edge of the solar system, a blazing thermal boundary in what was supposed to be the cold, dead emptiness of deep space. Scientists had not predicted this. Nothing in the pre-Voyager models had suggested that the transition from our solar bubble into interstellar space would involve passing through what amounts to a scorching thermal barrier. And yet, there it was, confirmed by instruments on both spacecraft, undeniable in the data streaming back across billions of miles. This is not chaos, this is structure. Structure nobody had put on the map before Voyager went and found it. And the deeper Voyager went, the stranger the map became. Once it crossed that boundary and entered what scientists call the very local interstellar medium, the immediate cosmic neighborhood just outside our solar bubble, it began detecting something that kept the research teams up at night. In 2020, Voyager 1's magnetometer registered an abrupt jump in the intensity of the magnetic fields embedded in the tenuous interstellar plasma, while its plasma detector simultaneously measured a rise in plasma density. Now, surges like these had been seen before, and each time before, they had faded back to normal levels after a few months. Scientists had a reasonable explanation. Powerful eruptions from the sun would smash against the boundary of the heliosphere, send ripple effects outward, compress the interstellar plasma momentarily, and then the disturbance would dissipate. Like a wave hitting a seawall, the energy would eventually cancel out. But here is where everything changes. The anomalies that began in 2020 did not abate, leading some mission scientists to question whether they originated with the Sun at all. Let that sink in. The leading scientists on the Voyager mission, people who have spent decades studying this spacecraft and the physics of deep space, looked at the data coming back and began seriously questioning whether the disturbances Voyager was recording were even caused by the Sun. If not the Sun, then what? That question, as of right now, does not have a clean answer, and that uncertainty is not a failure of science. It is science working exactly as it should, reaching the frontier of human knowledge and finding that the frontier is much stranger and much more complex than anyone had previously mapped. But it also means that Voyager, in its final operational years, may have detected something out there in the interstellar medium that we still cannot fully explain. Scientific research published in 2026, focusing on Voyager 1's magnetic field observations, found that the compressible component of the magnetic field showed a temporary resurgence of intermittency in late 2024 before stabilizing again in early 2025. With researchers concluding that Voyager 1 has not yet transitioned into a pristine interstellar medium entirely devoid of solar influence, but instead remains within a perturbed, very local interstellar medium environment characterized by weakening but persistent intermittent turbulence. In plain language, the interstellar space Voyager is moving through is not calm. It is turbulent. It is complex. It is being actively shaped by forces we are still working to understand. The universe beyond our solar system is not the quiet, empty void that generations of scientists assumed. It is dynamic. It is alive with activity. And Voyager is the only instrument humanity currently has positioned to measure any of it directly. But here is where the story takes its most unsettling turn. Because even as Voyager was making these discoveries, even as it was sending back irreplaceable data from the only place any human machine has ever been, it was dying. Slowly, instrument by instrument, piece by piece, it was going dark. Voyager 1 uses 3 radioisotope thermoelectric generators, devices that convert heat from decaying plutonium-238 into electricity, and after nearly 50 years of continuous operation, these generators are running critically low on power, declining by about 4 watts per year, producing less than half their original output as of April 2026. When Voyager launched in 1977, its power systems generated approximately 470 watts. That was already a modest amount, comparable to a few household light bulbs. But it was enough to run the spacecraft's full suite of instruments, its computers, its communication systems, its heaters, everything. Now, nearly 5 decades later, the generators are producing a fraction of that. And every watt that disappears is a decision. Every watt that disappears forces the engineers at NASA's Jet Propulsion Laboratory to choose what stays on and what goes dark forever. The cameras were shut down decades ago after their work was done. The plasma science instrument was shut off due to degraded performance. The ultraviolet spectrometer lasted far longer than its original planetary mission, but was eventually turned off. And the power cuts reached the instruments most closely tied to interstellar science. One by one, the scientific eyes of humanity's most distant explorer have been going blind. And the people making these decisions are not making them casually. They are making them with the full weight of knowing that once an instrument on Voyager goes off, it may never come back on. The machine is too far away, operating in too cold an environment, with too little power margin to guarantee that any system, once shut down, can be successfully restarted. Years ago, the Voyager science and engineering team sat down together and agreed on the order in which they would shut off parts of the spacecraft, ensuring the mission could continue to conduct its unique science for as long as possible. Of the 10 identical sets of instruments each spacecraft carries, 7 have been shut off, 7 out of 10 instruments gone, and the pace of shutdowns has been accelerating. NASA shut down Voyager 1's cosmic ray subsystem in February 2025, and then shut down the low-energy charged particles experiment on April 17, 2026. 2 instruments gone within 14 months. That is the rhythm of a mission entering its final chapter. What most people are not seeing is that these shutdowns are not just administrative decisions. They represent the permanent loss of our only window into specific physical phenomena in interstellar space. When the cosmic ray subsystem went dark, humanity lost its direct, real-time measurement of high-energy galactic cosmic rays from within the interstellar medium. Those measurements cannot currently be obtained from any other source. There is no backup. There is no replacement mission. There is just the silence where the data used to be. On NASA's current Voyager status page, updated April 17, 2026, only 2 Voyager 1 science instruments remain on, the magnetometer and the plasma wave subsystem. 2 instruments, on a spacecraft that launched with 10 complete scientific payloads. 2 survivors, still functioning, still transmitting, still doing science from the most remote location any human-built object has ever occupied. And even those 2 instruments are now operating on borrowed time, kept alive through engineering decisions of extraordinary precision and consequence. Managing what is left requires a kind of technical balancing act that has no real precedent in the history of spaceflight. Turning off instruments and heaters in the frigid temperatures of interstellar space risks chilling the probes beyond repair. If the fuel lines freeze, the spacecraft would lose the ability to keep their antennas pointed toward Earth, and NASA teams would lose contact with them, effectively ending the missions. This is the razor's edge that the Voyager engineering team walks every single day. Conserve too aggressively, and you might freeze a fuel line. Be too conservative with the shutdown schedule, and you drain the power before you've extracted the last crucial years of scientific data. Either mistake is permanent. Either mistake means silence. And silence, when you're talking about Voyager 1, means something that cannot be recovered. From May 2025 through February 2026, Deep Space Station 43, a 230-foot wide antenna in Canberra, Australia, the only dish with enough signal power to send commands to the Voyagers, was offline for most of that time, undergoing critical upgrades. Think about the position that put the mission in. The only antenna on Earth capable of communicating with Voyager was unavailable for the better part of a year. During that window, engineers could not send new commands. They could not intervene if something went wrong. Voyager was out there, alone, billions of miles away, and the one telephone line connecting it to Earth was temporarily cut. The engineers had prepared for this. They had preloaded commands. They had done everything they could to set the spacecraft up for autonomous operation during the blackout period, but the vulnerability of the situation was stark. Voyager's survival was not guaranteed even before the power problem. Now add the communication blackout on top of it, and you begin to understand how precarious the final years of this mission truly are. And yet, against all reasonable expectation, Voyager kept going. And what the mission's propulsion lead described as yet another miracle save, engineers found a way to revive Voyager 1's backup thrusters, systems that had been considered effectively dead, by diagnosing an unexpected technical cause that turned out to be fixable. Dead thrusters, brought back to life across a communication distance of 15 billion miles. The team sent a command, waited nearly 22 hours for it to arrive, waited another 22 hours for the response to come back, and then discovered that what they had tried had actually worked. A repair executed over a distance that makes any previous conception of remote operation look laughably modest. This is the kind of engineering that does not make the front page of newspapers, but it is the kind of engineering that has kept humanity's most important scientific emissary alive long past any reasonable expectation of its operational life. Now, the engineers are preparing for something they are calling the Big Bang, not a reference to the origin of the universe, a reference to their most ambitious, most consequential power management maneuver yet. The Big Bang maneuver involves turning off a group of powered devices simultaneously and activating low-power alternatives to keep the spacecraft warm enough to continue gathering science data, with engineers planning to implement it on Voyager 2 first, since it has slightly more power and is closer to Earth. This is a test run. Before they attempt this maneuver on Voyager 1, the more distant, more power-depleted, more critical of the two spacecraft, they're going to try it on its twin. Tests are scheduled for May and June 2026 on Voyager 2. If successful, the same approach will be applied to Voyager 1, no earlier than July 2026. And if it works, if the Big Bang successfully extends the mission's operational life, there is even a possibility that Voyager 1's recently shut down LECP instrument could be turned back on in the future. That instrument, the low-energy charged particles experiment, which measured the very structure of interstellar space, could potentially be revived. Scientists could get back measurements they thought they had permanently lost, but this is contingent on everything going right. On a spacecraft nearly 50 years old, operating in the coldest, most remote environment in human history, running on less than half its original power, communicating through a signal so faint it requires the most sensitive listening equipment on Earth just to detect. The margin for error is essentially zero. NASA's current public updates suggest the Voyagers can continue returning limited science data into the late 2020s if power-saving measures keep working, though the Big Bang reconfiguration could extend that horizon, or introduce risks that cannot be fully undone at this distance. That phrase, cannot be fully undone, carries enormous weight when you understand the context. If the Big Bang maneuver destabilizes something on Voyager 1 that cannot be corrected by a remote command, the mission ends. Not gradually, not with a controlled shutdown. It ends without the option of a graceful conclusion. The engineers who have devoted careers to this spacecraft could find themselves watching the signal simply stop, knowing that whatever went wrong happened 47 years' worth of engineering legacy away, beyond any possibility of physical intervention. But here is what is easy to miss in all of this operational drama. Here is what gets lost when the conversation focuses on watts and instruments and thruster tests. The real story is what Voyager actually found out there, and why losing it matters so catastrophically for science. Recent observations from Voyager 1 have detected faint thermal emissions that indicate changes in plasma density as it moves deeper into the interstellar medium, with electron densities remaining relatively constant at about 0. 147 particles per cubic centimeter beyond 160 astronomical units from the Sun. 160 astronomical units. Each astronomical unit is roughly 93 million miles. The distance from the Earth to the Sun. Voyager is measuring the structure of space at a distance so vast that it takes light nearly 22 hours to travel that far. And what it is finding is that the interstellar medium is not uniform. It is not the same everywhere. It has structure, density gradients, regions of compression, regions of turbulence. The universe beyond our solar system has texture, and Voyager is the only instrument we have that can feel it directly. Voyager 1's plasma wave system detected a class of very weak narrowband plasma wave emissions persisting from 2017 onwards, enabling a continuously sampled measurement of the interstellar plasma density over roughly 10 astronomical units of interstellar space, revealing density fluctuations that trace interstellar turbulence between solar disturbance events. Before this discovery, scientists could only measure plasma density in interstellar space when there happened to be a solar event powerful enough to generate detectable oscillations in the medium. It was like trying to map the ocean floor by waiting for earthquakes to generate sonar reflections. Voyager's detection of these persistent, continuous plasma wave emissions meant that scientists could now map the interstellar medium's density in real time, continuously, without needing to wait for fortuitous events. It was a methodological revolution, and it was achieved not by a newly designed cutting-edge instrument, but by a piece of hardware built using 1970s technology, flying on a spacecraft that was supposed to last 4 years and has now lasted almost 50. The current measurements indicate that the interstellar density has been increasing further from the value it had just outside the heliopause, and the leading hypothesis is that interstellar material may be piling up near the heliosphere's boundary like snow in front of a snowplow. Think about what that image means physically. The Sun's protective bubble is moving through the interstellar medium, and as it moves, it is accumulating material in front of it. The interstellar medium is not simply sitting there passively while the heliosphere carves through it. There's an interaction, a dynamic physical process happening at the boundary, and that process is shaping the density profile of local interstellar space in ways that scientists are still working to fully model. Voyager is the only instrument giving us ground truth on this. Everything else, every telescope, every satellite, every theoretical model, is working with indirect evidence. Voyager is the source. In November 2026, Voyager 1 will be 1 light day from Earth, the first human-made object to reach this distance, meaning that if NASA sends a command at 8 in the morning on a Monday, Voyager's response will not arrive until Wednesday morning. A 2-day conversation lag, communicating with a machine using technology designed in the early years of the personal computer era, across a distance that makes every previous human achievement in exploration seem modest by comparison. And when that milestone arrives in November 2026, Voyager will be approaching its 50th anniversary of continuous flight. 50 years in space, not in orbit around Earth, not in the comfortable inner solar system, but in the interstellar medium, beyond the protective bubble of our own sun, sampling a universe that no other probe has ever directly touched. When Voyager 1 reaches 1 light day from Earth in November 2026, the next human-built object to surpass its distance does not yet exist. New Horizons is also heading outward, but it will take a very long time to reach comparable distances, and no successor mission is currently operating in interstellar space. No successor mission. When Voyager finally goes silent, there will be a gap in humanity's direct observation of the interstellar medium that cannot currently be filled. Every model, every simulation, every theoretical prediction about the nature of interstellar space will have to proceed without the calibration that only a direct measurement instrument can provide. Scientists will be working essentially in the dark, using the last known measurements Voyager provided as anchor points and projecting forward from there. And given how consistently Voyager has surprised scientists with what it actually found versus what they expected to find, those projections carry a level of uncertainty that is difficult to overstate. Voyager 1 remains the only spacecraft directly sampling interstellar space. It measures cosmic rays, charged particles, the magnetic field, and the plasma environment beyond the heliosphere, measurements that cannot currently be duplicated by any other mission. Even 1 additional year of data helps scientists better understand the interactions among the solar wind, the interstellar medium, and cosmic radiation, as well as the boundary of our solar system. 1 additional year. That is not an abstraction. That is potentially the difference between understanding and not understanding a physical phenomenon that determines the nature of the environment the entire solar system moves through. The heliosphere does not exist in isolation. It exists embedded in the interstellar medium, shaped by it, interacting with it constantly. And the nature of that interaction directly affects everything inside the heliosphere, including the radiation environment of Earth, including the cosmic ray flux that bombards the inner solar system, including the conditions that will eventually matter for any human attempt at interstellar travel. The end of Voyager 1's mission will arrive not with a dramatic explosion, but with power falling below minimum operating thresholds, and NASA shutting down the final instrument, with the final transmitter eventually losing power. The signal will not cut out dramatically. There will be no sudden event. There will be a gradual degradation, a slow dimming of the carrier wave, engineers watching the signal-to-noise ratio deteriorate, and then a point, quiet, undramatic, devastating in its understatement, where the data stops, where the most extraordinary scientific instrument ever sent into space finally ceases to report, where 48 years of continuous transmission across a distance so vast that signals take almost a full day to cross it simply ends. The radio signal may persist for a while as engineering communication, but the science mission will have ended. No more field measurements, no more plasma waves, no more direct sampling from a region only the Voyager probes have ever reached. The Deep Space Network antennas will keep listening, out of protocol and perhaps out of something that might be described as institutional grief. But there will be nothing to hear. The conversation that began in 1977, when human beings chose to send a part of themselves outward into the cosmos on the most optimistic errand in history, will have concluded. And what will be left is the data. Decades of measurements from places no human senses have ever directly perceived. A scientific archive of discoveries that surprised us, that challenged our models, that revealed a universe at the edges of our solar system that was stranger and more complex and more dynamic than anyone had mapped before Voyager went and measured it firsthand. But here's the question that lingers, the question that does not get a clean answer no matter how carefully you study the data. When Voyager's magnetometer began registering those persistent, unexplained anomalies in 2220, the ones that did not fade like previous disturbances, the ones that prompted mission scientists to question whether the sun was even the source, what exactly was it detecting? The latest scientific analysis indicates that Voyager 1 has not yet transitioned into a pristine interstellar medium entirely devoid of solar influence, but remains within a perturbed, very local interstellar medium environment characterized by weakening but persistent intermittent turbulence. Weakening but persistent. The turbulence is not gone. The anomalies have moderated, but they have not resolved. Voyager is still passing through something, some structured, agitated, physically complex region of local interstellar space that does not match the simple, uniform medium that earlier theoretical frameworks assumed. What is generating that turbulence? How far does it extend? What does it transition into as you move further from the heliosphere's boundary? These are questions that only continued Voyager observations can even begin to answer. And the window for those observations is closing, instrument by instrument, year by year, watt by watt. The Big Bang maneuver may buy some time. The engineer's extraordinary ingenuity may extract another year or two of science from hardware that was designed to last 4 years and has already lasted 50. But the end has a fixed address, and Voyager is moving toward it at 38,000 miles per hour. What did Voyager find in its final years? It found a universe at the edge of our solar system that was hotter than it should have been, more turbulent than models predicted, shaped by forces that science is still working to fully characterize. It found persistent plasma waves that revealed continuous structure in the interstellar medium. It found magnetic anomalies that may not have a solar origin. It found evidence of the heliosphere compressing interstellar material in front of it, building up a kind of cosmic bow wave whose full implications scientists have not yet mapped. It found, in short, that the boundary between our solar neighborhood and the rest of the universe is not a clean line, but a complex, dynamic, scientifically rich transition zone that we have barely begun to understand. And it found all of this while dying, while losing instruments one by one, while operating on power that would embarrass a household appliance, while communicating across distances so vast that each exchange of information takes nearly 2 days at the speed of light. This is not the story of a machine failing. This is the story of a machine succeeding so profoundly for so long against such extraordinary odds that its ending feels like something more than the conclusion of an engineering project. When Voyager 1 finally goes quiet, there will be no immediate replacement listening to plasma waves in the interstellar medium, no other operating spacecraft measuring the local galactic magnetic field from beyond the heliopause. There will be silence where Voyager's signal was. And in that silence, scientists will work with what they have. An archive of data from a 50-year mission that exceeded every expectation, answered questions nobody had thought to ask, and raised new questions that will define the frontier of space science for the next generation of researchers and missions. The real question, the one that should be keeping planetary scientists awake, the one that should be driving urgent conversations about successor missions, is not what Voyager found. It is what Voyager was about to find. Because if the anomalies it detected in its final years are any indication, if the turbulent, structured, complex interstellar environment it was still characterizing right up to the shutdown of its final science instruments is any guide, then there is something out there, something at the edge of our cosmic neighborhood, something in the very local interstellar medium that we have only glimpsed, something that does not yet have a name because we do not yet fully understand what it is, something that Voyager was still in the process of discovering when the power finally, inevitably, began to run out. And the unsettling truth is this: we may not have another instrument positioned to resume that investigation for decades, which means that whatever Voyager was on the verge of finding out there in those final dimming years in that turbulent and mysterious interstellar frontier, we may not know what it is for a very long time. Maybe a generation, maybe longer. The universe at the edge of our solar system is still talking. We are about to lose our only ear. What exactly was it saying?